In the previous lesson, I introduced you to 3D computer graphics and tessellation, which is the somewhat art form of creating a three-dimensional surface out of triangles. In this lesson, I want to expand the subject and talk about the unique challenges that we face in tessellating a seismic surface. I think it's appropriate to talk about tessellation early in this chapter, because as you work with the Explorer, you won't be directly aware of tessellation, but it's what the program is doing all the time, and how well it does it defines your experience with your seismic. This entire course is about visualization, and the goal of visualization is for us to gain a complete visual impression of an object. That's what we're after here. We want a complete visual impression of our seismic. We want to perceive it all. It's up to us, the experienced and knowledgeable viewers, to make sense of everything we see and decide what is important and what should be ignored. The display can't do that for us, and it shouldn't try. So visualization is about perceiving it all, and as you will see, when it comes to 3D visualization, tessellation is the key. And when it comes to tessellating seismic, as with all things seismic, if it looks simple, you aren't looking closely enough. You will probably have noticed that I began this chapter showing images that were decidedly non-seismic, and as you can see, I brought one back. I've done that for a reason, because I want to talk about the difference between tessellating a seismic surface and any other surface. What you're looking at is a digital elevation model produced by a company called Photosat in Vancouver. The program that produced it is called VTW, and I should know, because I wrote it. VTW is the precursor to the Seismic Terrain Explorer, and I developed many of my visualization techniques as I was writing it. Like seismic, the DEMs that Photosat produce are huge, containing sometimes on the order of 100 million elevation points. Rendering them efficiently was a challenge, but it was much simpler than rendering corresponding seismic lines, and I'll show you why. Digital elevation models are what I classify as low-frequency surfaces. Unfortunately, I don't have VTW anymore, so I can't show you a live example, but the DEM in this image is typical. As you can see, while it is a detailed model, the terrain changes very slowly. There are significant changes, but they are generally smooth and infrequent. By way of comparison, this is a seismic image that has similar number of points, but the terrain complexity is far more severe and dramatic. Seismic is, therefore, an extreme high-frequency surface. Terrain and most other 3D rendered objects are much lower frequency surfaces. This isn't a new concept for me. I realized it more than 10 years ago while I was working on my PhD in seismic visualization, and I did some FK examinations at the time. Here are two similarly sized surfaces. The first is an extraction from a much larger seismic line. The second is a digital elevation model from the Crow's Nest Pass on the Alberta-BC border. If we take these two datasets into the FK domain, you can see that the FK spectrum of the seismic is much broader than the corresponding spectrum of the elevation model. I've done this exercise with many other examples, and the results always come out like this. Seismic is, in my experience, the most information-rich data source in the world today. When you think of all the subtle amplitude changes and all the faults, dipping events and noise trains, it's hard to think of a more rapidly undulating surface. And yet, despite its complexity, we want to get a visual impression of it all. And that impression is defined by how well we tessellate the surface. So now, let me show you what's required to do it. The first line that we will look at is this one. It is the pre-stack wave equation depth migration of the Marmousi 2 model produced by Gary Martin. I'm using it because it clearly illustrates some of the difficulties we face when tessellating a seismic surface. I'll zoom in here and show you what I mean. As you can see, the events in general are rough and the steeply dipping events are extremely rough. This is a problem that is endemic with seismic. We record and process to capture frequencies and wave numbers, but we don't think about what we need to reconstruct the wave field. In this case, I am rendering only the recorded samples. The depth sample interval is 5 meters and the horizontal interval is 6.25 meters. Clearly, that resolution is not sufficient to render this surface correctly. To compensate for this, somewhat, I use a bicubic spline interpolator to smooth out the events, and as you can see, it's done a good job of smoothing, if not fixing the problem entirely. The subject here is tessellation, so let me show you now how this surface is tessellated, and to do that, I'll display it in what's called wireframe mode. This is what the raw surface looks like behind the scenes. I'm tessellating it using just the raw samples, so you get an idea of how many native triangles there are in this surface. One point to note is that if you're following along with me, because this is one of my example projects, you won't be able to do this. There's no reason to look at the seismic this way in a production environment, so I programmed it special, just for this video. You are looking now at the raw samples, but this isn't how I usually display my seismic. As I said earlier, I apply a bicubic spline interpolator, and I'll do that now. As you can see, there are a lot more triangles in this display. In fact, there are 16 times as many triangles in this display as there were in the raw sample display. You might think that this is excessive and that we can get away with fewer. In my experience, however, we can't. This type of on-the-fly resampling is necessary before we can begin to fully appreciate everything that seismic amplitudes have to tell us. So let me zoom out here so you can get some sense of the sheer volume of triangles that must be rendered in order to look at this display. In fact, it's not unusual for the Explorer to be rendering up to 100 million triangles in a frame. Given that there are only a maximum of 4 million pixels on the screen, this seems like overkill, but surprisingly it isn't. And I'll switch projects and show you why. This is line 12 from Peru Petro's Trujillo dataset, and it's one of my downloadable projects, so you can look at the line yourself. The total number of triangles being rendered in this scene exceeds 100 million, even though because of my adaptive tessellation, I'm not resampling because we're zoomed out too far. I will zoom in a little bit so you can see the data better. Normally, if you looked at a similarly sized DEM, you would decimate the number of samples being rendered for efficiency. But as I showed you earlier, because seismic is such a high frequency surface, rendering at even the raw sample interval produces an undersampled surface. If you decimate seismic below that, the visual effect severely degrades the experience. So to be effective, seismic must be resampled on the fly as needed, but it can never be subsampled below its native resolution. So yes, there may only be 2K or 4K pixels in this image, but to produce an effective image, we have to render all the samples, and that may exceed 100 million. So this has been a longer lesson than I intended, but I think it is critically important, because behind the scenes there is a critically important question about the validity of wave field reconstruction and visualization. The question is, if it's so important, then why haven't we done it before? Answering that question is why I started with Toy Story. In 1995, Toy Story rendered 2 million triangles per scene, and each scene took up to 3 hours to render on a factory of 127 high-speed computers. That was already 30 years into the digital seismic revolution, and yes, we should have reconstructed the wave-field all along. But seriously, what chance did we have? As I've shown you, to render seismic effectively, you may have to render tens or even hundreds of millions of triangles, 30 times a second. So the reason why we haven't done this before is that we simply couldn't. I'm not critical of the fact that we still use variable density and grayscale displays, because they served as essential placeholders for our seismic until the technology developed so we could move beyond them. The technology now exists, so let's be frank. It's time we did.